occasions. China had made great mathematical leaps, but the next great mathematical breakthroughs were to happen in a country lying to the southwest of China. A country that had a rich mathematical tradition that would change the face of maths forever. India's first great mathematical gift lay in the world of number. Like the Chinese, the Indians had discovered the mathematical benefits of the decimal place value system and were using it by the middle of the 3rd century AD. It's been suggested that the Indians learned the system from Chinese merchants travelling through India with their counting rods. Or they may well just have stumbled across it themselves. It's all such a long time ago that it's shrouded in mystery. We may never know how the Indians came up with their number system, but we do know that they refined and perfected it, creating the ancestors for the 9 numerals we use across the world today. Many rank the Indian system of counting as one of the greatest intellectual innovations of all time, developing into the closest thing we could call a universal language. But there was one number missing, and it was the Indians who would introduce it to the world. The earliest known recording of this new number dates from the 9th century, though it was probably in practical use for centuries before. This strange new numeral is engraved on the wall of a small temple in the fort of Gwalior in central India. So here we are, in one of the true holy sites of the mathematical world. And what I'm looking for is in this inscription written on the wall. Up here are some numbers, and here's the new number. It's 0. It's astonishing to think that before the Indians invented it, there was no number 0. To the ancient Greeks, it simply hadn't existed. To the Egyptians, Mesopotamians, and as we've seen, the Chinese, 0 had been in use, but as a placeholder, an empty space to show a 0 inside a number. The Indians transformed 0 from a mere placeholder into a number that made sense in its own right, a number for calculation, for investigation. This brilliant conceptual leap would revolutionise mathematics. Now, with just 10 digits, 0 to 9, it was suddenly possible to capture astronomically large numbers in an incredibly efficient way. But why did the Indians make this imaginative leap? Well, we'll never know for sure, but it's possible that the idea and symbol that the Indians used for 0 came from calculations they did with stones in the sand. When stones were removed from the calculation, a small round hole was left in its place, representing the movement from something to nothing. But perhaps there's also a cultural reason for the invention of 0. For the ancient Indians, the concepts of nothingness and eternity lay at the very heart of their belief system. In the religions of India, the universe was born out of nothingness, and nothingness is the ultimate goal of humanity. So it's perhaps not surprising that a culture that so enthusiastically embraced the void should be happy with the notion of zero.
The Indians even used the word for the philosophical idea of the void, shunya, to represent the new mathematical term zero. In the 7th century, the brilliant Indian mathematician Brahmagupta proved some of the essential properties of zero. Brahmagupta's rules about calculating with zero are taught in schools all over the world to this day. 1 plus 0 equals 1. 1 minus 0 equals 1. 1 times 0 is equal to 0.
But Brahmagupta came a cropper when he tried to do 1 divided by 0. After all, what number times 0 equals 1? It would require a new mathematical concept, that of infinity, to make sense of dividing by 0. And the breakthrough was made by a 12th century Indian mathematician called Bhaskara II. And it works like this. If I take a fruit and I divide it into halves, I get 2 pieces. So 1 divided by a half is 2. If I divide it into thirds, I get 3 pieces. So when I divide it into smaller and smaller fractions, I get more and more pieces. So ultimately, when I divide by a piece which is of 0 size, I'll have infinitely many pieces. So for Bhaskara, 1 divided by 0 is infinity.
But the Indians were to go further in their calculations with zero. For example, if you take 3 from 3 and get 0, what happens when you take 4 from 3? It looks like you have nothing. But the Indians recognised that this was a new sort of nothing, negative numbers. The Indians called them debts because they were perfect for solving equations like, if I have 3 batches of material and take 4 away, how many have I left?
This may seem odd and impractical, but that was the beauty of Indian mathematics. Their ability to come up with negative numbers and 0 was because they thought of numbers as abstract entities. They weren't just for counting and measuring pieces of cloth. They had a life of their own, floating free of the real world. This led to an explosion of mathematical ideas.
The Indians' abstract approach to mathematics soon revealed a new side to the problem of how to solve quadratic equations. That is, equations including numbers to the power of 2. Brahmagupta's understanding of negative numbers allowed him to see that quadratic equations always have 2 solutions, one of which could be negative.
Brahmagupta went even further, solving quadratic equations with 2 unknowns, a question which wouldn't be considered in the West until 1657, when the French mathematician Fermat challenged his colleagues with the same problem. Little did he know that they'd been beaten to a solution by Brahmagupta 1,000 years earlier.
Brahmagupta was beginning to find abstract ways of solving equations. But astonishingly, he was also developing a new mathematical language to express that abstraction. Brahmagupta was experimenting with ways of writing his equations down, using the initials of the names of different colours to represent unknowns in his equations.
A new mathematical language was coming to life, which would ultimately lead to the X's and Y's which fill today's mathematical journals.
But it wasn't just new notation that was being developed. Indian mathematicians were responsible for making fundamental new discoveries in the theory of trigonometry.